Thanks for the introduction. And I'm Zhongming Wang from Chongqing University. It's a joint work with Tao Xiang, Xiaoguo Li, Biwenchen, Chuan Ma, also from Chongqing University, and Guomin Yang, Rupert Deng from Singapore Management University. Okay, end-to-end encryption had been widely deployed in real-world messaging systems like WhatsApp, Signal, and iMessage. And unlike traceable security, end-to-end encryption conceals users' messages from the platform, thereby significantly enhancing users' privacy. Unfortunately, this also facilitates the spread of problematic messages, including misinformation and disinformation. And because the messages are encrypted, the platform cannot use conventional machine learning-based methods for moderation. Therefore, end-to-end encryption creates a tension between users' privacy and content moderation. Meanwhile, messaging forwarding is a significant feature of spreading information. And on WhatsApp, a message can be forwarded up to 5 chats at a time. And to restrict the spread of misinformation, WhatsApp limits the multiple forwarded message to be forwarded up to 1 chat at a time. However, this restriction applies to all the messages, including harmless memes and useful contents. So a better solution proposed is traceability for encrypted messaging, and it allows the platform to trace the dissemination path of user-reported messages. Currently, there are different lines of work that reveals the different parts of dissemination path to the platform after tracing. And message franking only reveals the last sender of the message to the platform. Message traceback reveals the entire dissemination path to the platform. In contrast, source tracing reveals only the originator of the message. And it's evident that there is a trade-off between traceability and privacy. Traceability aims for the platform to reveal the entire dissemination path of the information or reported message. In contrast, privacy wants the platform to learn nothing about the forwarding path of any message. And message traceback offers full traceability but no privacy, and it reveals the entire dissemination path. Source tracing offers good privacy but poor traceability, since it reveals only the originator. And here is the middle ground between the two works. So in this work, we trying to address the following question: is there a tracing policy that balances traceability and privacy? Our key observation is that a small group of users called influential spreaders significantly contribute to spread information. And these users act as amplifiers of information and are distributed on the determined paths of messages. For instance, according to the CCGT's report in 2021, 65% of anti-vaccine disinformation can be attributed to the disinformation dozen. And these messages are on WhatsApp, on Twitter, and Facebook. So the goal of our impact tracing is to identify these influential spreaders while preserving the privacy of non-influential users. And to implement impact tracing, we begin with a simple message franking scheme that only supports user reporting. In the messaging phase, the sender will randomly choose the tag key K, and it will generate a message tag from the tag key and a message. It next transmits the message tag key and a message tag to the platform, where the platform stores the message tag to its storage. And because the function f is a pseudo-random function, the platform learns nothing about the message from message tag. And to report a message, a recipient will submit the message tag key to the platform. The platform can verify this report by recomputing the message tag and check whether the tag is previously stored. And here, the message tag works as a commitment. It binds the user to its sender messages. Unfortunately, this method cannot enable tracing for forwarded messages, because when the users are forwarded messages, they are generate tag keys independently. So, for example, in here, the platform receives K3 from the reporter, but it cannot compute K2 from K3, because these two keys have no relationship. And this motivates us to find a solution to link these tag keys implicitly in messaging phase and allowing the platform to compute previous tag keys in reporting phase or tracing phase. And our solution is that we now let the sender to generate a tag key using tracing key by encryption. And that tracing key is calculated by combining a sender's secret identity key and the recipient's public identity. And it implicitly binds the communication party's identity to the tracing key. And once the initial tag key is chosen, all the subsequent tag keys are deterministically generated along with the forwarding path. And so now in the reporting then tracing phase, the plaintiff can also start at key 3, but it now can compute previous tag keys because it knows all the user's secret identity key and the public identity. And this allows the platform to check whether a user has forwarded the reported message when tracing. And in more detail, in the messaging phase, the users will forward messages along with traceability data that include the message tag and tag key in our last slide. And the platform will collect users' communications and store message tags. When a message is reported with the collected information, the platform will start at the reporting user, and it will first check whether the neighbors of this user have forwarded the message by computing message tags and check the existence of their tags. And for identified forwarders, it will include them into the next round of computation and do these operations recursively until no new forwarder found. So now we obtain a message traceback scheme that reveals the exact forward graph to the platform after tracing. Next, we employ random response mechanism to protect the privacy of non-influential users. We introduce an additional tag server for storing message tags. Naturally, now during tracing, the platform must query the tag server for existence of message tags. And the tag server will respond to the queries with random noise. For example, if a tag exists, it will return 1. But if the tag not exists, it will return 1 with some probability. And this probability will introduce random noise to the tracing results. The platform will now only obtain a noised graph instead of the actual forward graph after tracing. And but the goal of our encrypted tracing is to identify influential spreaders. So we design a decoding algorithm to uncover influential spreaders from the noised graph. And the intuition behind our decoding algorithm is that the forward graph is generated by messaging forwarding. So there are some relationships between the nodes in the graph. Like a node in the graph should have only one parent node. And these relationships, we can mitigate some noise that is introduced in our last slide to help us to identify influential spreaders. But this mitigation of noise doesn't violate our privacy protection for non-influential users. We proved that the noised graph produced by our fuzzy traceback scheme satisfies individualized differential privacy. And this means less influential users will be obscured by our introduced noise, while influential spreader will be accurately identified by our decoding algorithm. And we also analyze our results in experiment and please see our paper for more detail. And for performance evaluation, we compared our work with previous schemes and compared to the SOTA tracing scheme, our work reduced 70% bandwidth overhead, and compared to the traceback scheme, our work reduced 94% storage overhead. And for the runtime, our work can trace a graph with 4,000 edges within 15 seconds. And it can also transmit 1 kilobyte message within 0.3 milliseconds. So in summary, in this work, we introduced impact tracing, a tracing scheme that balances traceability and privacy. To implement impact tracing, we design fuzzy traceback and decoding algorithm. We also formally analyze security, privacy, and utility of our design. And our code is open source at GitHub, so you can scan for the code. And that's it. Any questions?
Any questions? Please come over here to the mic. So while people think about if they realize their questions, so what to ask you? So your solution is identifying the sender, only the influencer that are sending a lot of messages.
Yeah.
But supposing that the influencer wants to be not identified, can they do some stuff to avoid identification, like using Sybil identities, or right, and sending you via multiple Sybil entities and stuff like that? Would your solution be able to handle that?
Handle what? Can you say it again?
Using Sybil identities, like instead of having one identity, I will have multiple identities in the system, multiple accounts, and then I will send to multiple accounts, and each of these will send to multiple accounts, and then I will send to all of the people, instead of having a large fan out for myself, right?
You mean they can use multiple accounts to spread messages?
Yes, so I will use multiple accounts, and then I will send to these accounts, and the accounts will send to my multiple friends.
So for our paper, because there is some cost when you need to create an account that with many friends on WhatsApp, like something like that. Because it's a social network, it's not social media. You cannot just send a message to anyone you want. So there are some costs. So we assume, and the users are like they already have many friends on the application, and so it will use the same account to spread the messages.
Right, but this is in your scenario. You're talking about this user sending the message to a particular recipient, right? It's you send to a particular recipient.
Yeah. Send to particular recipient. Yeah.
Right. It's not like you're sending to all of your friends, in which case, of course, you don't have control. So you are sending to particular recipients, right? If
you are sending to a particular recipient, your recipient will not report the message, right? So we are focusing on the one who will be reported. Yeah, must be reported.
Right. So you focus on the case that the same entity is sending to all the recipients.
Yeah.
Great.
Hi, thanks for the talk. I really like the idea of storing these tags as opposed to macking them as you do in normal franking. But I was wondering, so like, I think you said you store like 6 bytes per message, like on the tag server.
Yeah.
Like for the volume of messages that a service like WhatsApp receives, have you given any thought into like what sort of like reasonable window of like previous tags could you store, and like would it break your system if like you sort of cut off history after a certain point?
Yeah, that's a good question. So in our paper, we just assume the spread window is 1 month, so you can just store 1 month messages, and I know we don't have some recordings, but we believe that. So for messages, you don't need to trace a message that is far beyond, because you can trace a message in 1 year before, right? Normally you just trace a message in like 1 month, so we just assume it's 1 month.
I see.
Yeah.
Do you have any sort of idea of like what size database WhatsApp would need in order to implement a system like this?
I guess 1 terabyte, maybe.
Okay.
Yeah.
Thank you.
Thank you.
Let's thank the speaker.